Thank you very much. So I'm going to be talking about my open source project, which is very much experimental and challenging for everybody to understand and use, including myself. But it promises, should have been full screen, but it's not doing full screen. Okay. So this paradigm is called the chemical machine. Okay, you've never heard of it. But this paradigm promises to implement everything in 15 lines of code or less. It's so declarative that your programs are correct by construction. They're obviously correct. There's no need to debug anything. And the only problem is you need to start thinking in a new way. Okay, so that's my goal today, is to explain how to think in this new way in different metaphors and show code that uses this. I have presented this before. In this presentation today, there is a significant new element, which is distributed programming. So the previous implementations that I had were concurrent programming only, which means you can implement any concurrent task in 15 lines of code or less. But now you can implement any distributed concurrent task in 15 lines of code or less. So that's a new element in this presentation. Not in my talk will be any kind of academic theory. And I'm formerly a theoretical physicist, so I can bash academics if I want to. This chemical machine paradigm is based on something called joint calculus. So can I ask how many people have ever heard of that? 1, 2 in the back. Right. Not a lot of people. And I can't blame you for not knowing about joint calculus, because if you even get this idea of looking it up in the Wikipedia, then you will read something that's like this. Communication occurs only on defined names, and replicated reception is syntactically merged into the definition. Okay, so this is completely unhelpful. Okay, I don't really understand what they wanted to say in this web page. Although I have implemented this paradigm several times, I know very well what this is supposed to do, how it's working, but I don't understand this jargon, and they don't care to explain it to you. So let me just close this tab. It's so useless. Just so useless. So that's basically what my talk is going to be about. We all know that imperative concurrency and parallelism is very hard, and we don't want to do that because there are all kinds of problems with reasoning about mutable state, reasoning about processes that run at the same time. It's very hard to test. You have non-deterministic behavior at runtime. There's never enough testing, basically. So you have all kinds of race conditions, deadlocks, live locks. People don't want to program in threads and callbacks and semaphores. And people have other approaches. People have these more declarative approaches to concurrency and parallelism, which I stratify into 4 complexity classes. My classification is from top to bottom, increasing complexity. So the easiest way is synchronous parallelism. And this is MapReduce, this is Spark, this is Scala parallel collections, where you split your task into pieces. Each piece is separate and independent. You run it, and you merge the results. From the type theory point of view, this is applicative functor. Applicative functors are well known to be easily runnable in parallel because computations are independent of each other. The next complexity class is a synchronous streaming graph, or without cycles. And that is realized, for instance, with Future, async await, and various reactive frameworks, streaming frameworks. There are many, many libraries now that do this. From the type theory point of view, this is a monadic functor, like Future is a monadic functor. And you can see that it's strictly more powerful than applicative. And so this is really a different complexity class from the point of view of type theory already, so that's not just arbitrary distinction. The next complexity class is unrestricted streaming, where your graph can be cyclic, it can be parallelizing, forking and joining parallel things and so on, but it's still a graph. There are different implementations of this. We will hear in this conference, I'm sure, about FS2, ZIO, and other such things. Flink is another one. Akka streams can probably do this too. And from the type theory point of view, this is a little more complicated than just a monad. It's a recursive monad, so the graph can feed itself asynchronously. And the final level of complexity is unrestricted concurrency, which means any kind of process can start at any time, wait for anything, and start other processes or terminate them or whatever. It's not a graph, it's not a stream, it's more complicated than that. I have no idea what type class that means. I don't want to try to say that. And yet more complicated is distributed computing. So on top of all that, you need to coordinate between different partitions of the network and so on. Consensus, cluster discovery, all that is another layer of complexity on top of this fourth layer, which I call unrestricted concurrency. And I would like just to mention that Apache Zookeeper and etcd and other such, maybe other things like Consul, they provide distributed coordination as a service. And that's what I'm going to be using as implementation for my library. But this is just an aside. So let me first start with ordinary concurrency. So the example of concurrency is the dining philosophers problem. Can I ask who does not know about dining philosophers problem? Who has not heard about it? 1, 2, 3. That's excellent. I'm not going to have a lot of trouble then. So basically, these philosophers, whom you can easily recognize by their faces, they have resource contention. So they eat and think concurrently and in parallel, but they have resource contention. They're contending on the forks. And so this is a problem that is, in my opinion, it is not a graph. It's not a stream. It is more complicated than that. I don't know how to prove mathematically that this cannot be implemented as, say, an expression of type future of x, where x is some type in Scala. I don't know. Maybe you can, maybe you cannot. In my intuition, this is more complicated than a stream, because you have resource contention. Stream without resource contention is less complicated than a stream with resource contention. So what I call unrestricted concurrency, you can think it's more than stream because it has resource contention at the same time as it has concurrency. Now, in different programming languages, I wanted to just show very quickly the solution. Where is this? Oh. Right. So there is this great website called Rosetta Code, and it has solutions for different programming problems in very different programming languages. So you see a lot of people contribute their favorite programming languages. So for example, let's take, I don't know, F#. Strategy, work, waiting, forks, philosopher, waiter, do, async, sleep, kind of complicated. Anyway, C++ is much worse. So that's not easy to simulate this problem, this dining philosophers. And let me show you this solution. Fits on one screen. It's certainly less than 15 lines of code. Is it? Kind of, yeah, almost. Yeah, I have 5, 5, 4 up there, and 1. Yeah, 15 lines of code. Yeah, so that is the chemical machine paradigm. If you can recognize very easily, it's less than 15 lines of code. And this solution is in the language called JoCamel, which is a fork of OCaml to implement the chemical machine. And you see, this solution is completely declarative. It just says that one philosopher and two forks leads to the eating process, and two forks are released, and philosopher is not hungry. And then a non-hungry philosopher leads to a thinking process and a hungry philosopher. That's your declaration. That's your specification of what you want to do. And this is actually executable. This runs and prints the philosopher's thinking and eating and so on. So the chemical machine code is purely declarative in this sense. It's a domain-specific language for concurrency. Unfortunately, because of insufficient documentation, and it's a fairly new paradigm, nobody knows about it. So I'm trying to spread the good word. And I'm trying to show that you can program, or at least you can think about concurrency. Maybe this is, you don't want to use this in production maybe, because it's my side project, which is not supported. But it will make you think about concurrency in a much clearer way. Once you learn how to think in this way, you can always do other things. So in order to explain the chemical machine paradigm, I have three different metaphors. The first, the easiest one perhaps, is to compare it with Amazon Lambda. And Amazon Lambda is almost the chemical machine, except for one feature. So what does Amazon Lambda do? It waits for some kind of signal that signals that the data is here. Data has arrived. Then it runs a computation on that data. The output data is pushed back into the system, and it might be another trigger when that happens. Add two requirements. One, that a Lambda should be able to wait for several triggers at once, not just one trigger, but several triggers at once. Two, when the one or more triggers arrive, they're consumed atomically. So if two more Lambdas can wait on the same trigger and contend on it, only one gets the data and the other doesn't. Now that could be quite difficult to implement actually in Amazon's distributed setting. I don't know, maybe it is easy, maybe, I don't think it's easy, but what do I know? If you do that, then instead of Amazon Lambda, you get Amazon Pi. I'm making a pun here on pi calculus. You get basically unrestricted concurrency. With current Amazon, as far as I know, they do not allow you to have multiple triggers. That is streaming. With this extra feature, it becomes fourth level of concurrency, unrestricted. Second metaphor is compared with actor model. I assume everybody knows actor model here. Again, actor model is very powerful, but we need to modify it in a few ways so that we can get the chemical machine out of it. And that helps you think about the chemical machine. First modification. Actors are created automatically by the system. You don't create actors. You create props, so to speak. You just create the body, the function body of the author, of the actor, but not instance, not actual actor ref. You don't manipulate actor refs. They're all automatic. And they're created automatically in parallel whenever messages arrive. So you actually send messages to mailboxes, and when messages arrive, automatically the system will make actors for you. And actors may wait atomically for messages in several different mailboxes, consume several messages at once, start, and then disappear. So from these requirements, I can logically derive that, for instance, instances of actors must be stateless, and all you do is you define mailboxes and computations. So here's a comparison. So ACA code roughly looks like this. You declare an actor reference, and the actor receives a message and does something, receives a message and does something, and you send messages. In my library called Chemist, this is the actual Scala syntax of the DSL. Very similar, except you can have more than one receive statement, so to speak, at once. So you receive B and C. So B and C are mailbox references. A is another mailbox reference. X, Y, Z are values on messages. So this function will consume X and do something with it, and this function will consume Y and Z and do something with it. And then you send messages to A, B, and C. So you send messages to mailboxes and not to specific actor instances. Yes?
So from my understanding of the actor model, actors receive messages in mailboxes kind of serially? Like there's no notion of receiving two messages at one time? What is the notion of receiving two messages like at the same time?
So the question is how do we understand the notion of receiving two messages at the same time, whereas in the actor model, messages are linearly received one at a time and processed one at a time. So you think of different mailboxes. So each mailbox gets one message at a time, but you are now allowed to wait on two mailboxes at the same time. And so when one mailbox has a message and the other does not, you don't do anything. You wait until the other has a message too, and then you grab two messages atomically at once. Yes?
So using this example, mailbox B, let's say you have one chemical process that can group B and C, another one that can group B and D, and B is emitted first. Does one of these two grab it and hold it, or is the B available to the first one that has a C or D available?
Yeah, so the question is, how do we handle contention? If one chemist actor, so to speak, waits on B and C and the other waits on B and D, and we get a B message in, what happens? Nothing happens until at least one of these gets all the data it needs, and then it's non-deterministic. Now, all actor programs can be straightforwardly translated into this.
Does the runtime ensure that the receive of two messages is atomic when it's dispatched to a agent or whatever it's called?
So these are called reactions. I'll show you the chemical metaphor in a second. Yeah, so the question is, do you ensure atomicity when you consume messages? So you can specify what you're waiting for, one or more messages. All of them are consumed atomically at once. And it is the scheduler's job, not your code, but the scheduler, the runtime's job to ensure that this works. Contention, non-determinism, it needs to be consistent. Finally, let me look at the chemical metaphor. So in the chemistry, in real life, molecules meet, like in this chemical reaction. I hope everybody knows what these symbols mean. In real life, molecules meet randomly. So imagine some kind of chemical reactor, and all we do is stir. And the molecules just randomly meet each other and start reacting. Nobody is telling them to wait or anything. They're just completely naturally distributed, concurrent. That's how we want our programs to be. Naturally distributed, concurrent, parallel. We don't want to tell each molecule to, oh, wait, we need this process, this thread. No, I don't want to do this. I just want to say what reactions exist. In nature, that's not what happens. Nature knows reactions, and it just runs. That's what we want to do. We want to have our computations run as naturally, concurrently, and parallel, and distributed as they do in real life. So to begin doing this, first we go from real chemistry to abstract chemistry, which means we just declare molecules of any kind and reactions of any kind. We don't care about real physics or real chemistry. So program code just defines our molecules A, B, C, and these laws. For example, A plus B goes to A. Whatever, it doesn't matter. In real life, of course, this cannot happen, but it doesn't matter. The runtime system will grab these laws, look at them, then it will simulate this. I have an A, I have an A, I have a B. Oh, I can run the first one. Let's run it. And then just keep doing that. A simulator can be implemented quite easily in any language, and I've done this in Objective-C, I've done this in Java. It runs, it's pretty easy. Now, in order to put this to use, you need to actually compute something. And the key idea is that each molecule needs to carry a value on it. So these are not just molecules, they're actually containers for values. And these values are now concurrent data. They can float in this concurrent world, wait to be consumed. Each reaction will consume, for example, A and B, but they now will consume the value on A and the value on B. When it emits A at the end, it needs to put a value on A, say Z. Where would this Z come from? Well, obviously, it needs to be computed from X and Y. So there you have a function from X and Y which corresponds to each reaction. Naturally, therefore, your program becomes a specification of molecules and their data types and a number of functions that take inputs and produce outputs and put these outputs on some molecules and take the inputs from some molecules. Here's the actual syntax in my Chemist DSL for this kind of program. Reactions are partial functions in the Scala syntax. This plus is the chemical plus, is not really an operation. It's just a separator. I'm taking A with value X, and I'm taking also B with value Y. I'm making a computation, and I'm emitting A with value Z. Very concise. Yes?
What happens when the requirements for two different functions are met? How do you choose?
So question is, what happens when the requirements are met for two different functions, which means data is available for two different computations to start. Which one will start? Non-deterministic. It is up to you to, like in nature, what happens when molecules can react this way or that way? They just do whatever they feel like. It's up to you, like it is up to the chemical engineer, to design the process so that the correct molecules come out. And it's always possible. But otherwise, it's non-deterministic. Sometimes it's good to have non-determinism in your code because you don't care in what order certain things are computed, but it is necessary to design everything such that the results are deterministic, of course. So basically, we need to learn how to think in molecules or concurrent data and reactions. To compare this with the actor model very quickly, actors are similar to this, but you still have to reason about instances of actors. I create instances of actors. And this is like saying, I compute 5 times 6 plus 7. I need to have an instance of plus. How many did I already allocate? And an instance of times. Because I have 5 times 6. I need an instance of time. Do I have already an instance of time? Can I send it to? You don't think like this. You just say 5 times 6 plus 7. You don't think about how many instances of plus you have. Similarly, in the chemical machine, you don't think about instances of actors. You specify your computation. There's no state, there's no supervision, there's no life cycle, there's no dead letter, there's no router, there's none of this. And the code is typically several times shorter than Akka code as a result. I will be boasting this throughout this code. Here's one first example. Okay, throttling. Oh, sorry, there's a question.
I'm just wondering, how do you manage the complexity when you have like hundreds of rules? Like, how do you, I don't know if you've like gotten to that, but how do you like?
The question is, how do I manage complexity if I have a lot of reactions? I have a lot of these computations. Each of the computations is a local value. I can put them in local scopes, in different modules. I can think about one of them at a time. So it is certainly, it's just like modularizing your program. You split it into independent parts. So you see there's a concept of a reaction site, which is this site function. And each site is independent. It runs independently on its own thread pool. And you think about that site as something that contains on its own input molecules independently of all others. So that's how you manage the complexity. Each little reaction site has maybe a couple of reactions. You think about them, and you think only about them. You don't have this spaghetti code of all kinds of things connected to everything else. Let me just show you this example. You will see how this is managed. So the task is I'm trying to throttle emission of a signal. So in the chemical machine, there's only one way to send a signal. It is to emit a molecule, emit data on the molecule. Suppose I have some molecule S, I want to throttle it. So I don't want to be emitted S too many times. I need some minimum delay. How do I do that? I make another molecule called R, which can be emitted at will. But when you emit R, S will be emitted with throttling every time. So R has a value on it called X with type X. I define a new molecule called R. I define a new molecule called enable, because the only way to prevent a reaction from happening is to withhold input molecules. Once you have input molecules in your chemical reactor, nothing can tell them not to react to each other. The only way to stop or delay something is to withhold input. So therefore, I create an auxiliary input, which I call enable, which doesn't have any value, it's just a unit value on it. But I withhold it until I'm ready to run the reaction. Then I define a reaction, which takes R, takes enable, it emits the S, and then it sleeps for this interval, and then it emits enable. So enable is emitted only after a sleep. While it is sleeping, somebody could have emitted 1,000,000 Rs, but no reaction will start, because enable isn't there. That's how you think. What molecules are present? When are they present? Everything will work. Your computation will start. But what are present? And what do you have enough of those? How do you prevent them from being emitted? Second thing, you see this is a function. It's a Scala function, def. So all of these things are defined in its local scope and it's completely invisible outside. Nobody can screw up with this. It's sealed. You return R, which means R is of type M of X, which is molecule emitter with values of type X. So whoever calls this throttle gets an R out, but they don't get enable out. They cannot screw up with this logic. So I guarantee that enable is emitted once initially in here, and nobody else can ever emit enable because it's in the local scope. So in this way, I have local reactions, local molecules, and I carefully separate the scopes. Note there are no threads, no semaphores, no locks, no mutable state, and everything works in far less than 15 lines of code, whereas all these other implementations in these other great libraries are much longer. Yes?
So the reaction consequences are not atomic, right? So
They're not.
They're not atomic, it's the action gets implemented, it gets emitted first, and then we fall asleep.
This is asynchronous. Emission is asynchronous.
So the throttling depends on there being one enable molecule at any time, right?
Correct.
So what happens when that machine catches on fire?
I don't understand. Catches on fire?
We emit the S and then we fall asleep and the machine catches on fire and we never re-enable, we never re-emit and enable. Like, isn't the whole thing going to stop then?
So the question is, what happens if the process crashes and this enable molecule is never emitted? And we pile up the R, and it's not, yeah, it's a deadlock. It's a deadlock. So yeah, if things crash, yeah, you get a deadlock in this case. All right, let me just jump through a few examples. This is MapReduce. ACA is a lot longer. This is parallel merge sort. ACA is longer. This is dining Philosophers. And I have a lot more examples. And ACA is longer. So if this were implemented really well and really efficiently, which I'm trying to do, but I'm just one person, and it's an open source project that I do in my spare time. If this were really efficient, I would never touch ACA again, okay? Because I don't want to write 200 lines of code if I can write 15 or less. And I said 15 or less. Anything you want to do, you do 15 or less. So reasoning is very easy. You just think about what molecules exist and what data is available for computations. You don't think about processes run concurrently or not. And okay, let me just before I go to my distributed. So this I already explained in previous presentations. Now, you see, if you look at when certain concepts were invented and when they were adopted by the industry, there's about a 40-year gap. 38.2-year gap, right? So 0.2 years is like 11 weeks. So 38 years and 11 weeks, you have to wait. And at the end of the 11th week, the industry says, great, we're all going to use it, like streaming, closures, you know, every programming language has a Lambda now. Every one, even like C++, right? Anyway, I've got a lot of stuff I'm skipping here. Has anyone heard of Petri Nets? More people heard of them. The chemical machine implements a very rich version of Petri Net. It's one-to-one, and it's got more features. Molecules are values, reactions are values. You can put, you know, channels and channels and channels, whatever you want. It's very, very flexible. And the Petri Net can be translated into a chemical machine very easily. Okay, new stuff. I've got 5 minutes before questions, but I've got already a lot of questions answered, hopefully. New stuff, distributed chemical machine. I figured out how to do distributed programming in the same model, 15 lines of code or less. Here's how it works. You just say, this molecule is distributed. Instead of M, so M is this constructor for a molecule, I do DM, which is a distributed molecule constructor. That's it. Now this data is distributed. That's it. Oh yeah, and you have to put an implicit val with a cluster config, which is a data structure that shows how to connect to the cluster. And it's a zookeeper instance, and you just connect to it. You're done. That's it. The language is modified by adding the concept of a distributed molecule, which means data. So previously we had a concept of molecule, which is data that is automatically concurrent. It is ready to be consumed by whoever is there and whatever you define. Now we have a concept of distributed molecule, data that is ready to be consumed by any peer on the cluster. And that's it. That's the only concept. Now you know everything. You can just go on and program. I don't have to explain anything more to you. This is the entire language. Here's an example of how to do distributed MapReduce, 15 lines of code or less. And akka, of course, is 400 lines of code. Who would ever write that? There are details that I'm not going to be able to explain in the limited time, but one important thing, yeah, distributed cache, 10 lines of code. Distributed peer-to-peer chat, 15 lines of code. akka code is longer. The main interesting things about this concept is that every peer operates in the same way. It's as if you have this chemical reactor that is just distributed between different plants, and they all exchange the soup, the solution with each other. They exchange the solution in a random way. So whoever is free to start processing, they will just grab some molecules, do the processing, put the molecules back into the cluster, and then grab some other molecule, do the processing, put it back. There is no master worker, driver, nothing. It's just everything is completely symmetric. If you disconnect from the cluster and connect again, you just keep going. Nobody knows about you. My code does not know how many nodes are in the cluster, how to connect to them. This is the entire code. And you reason about it in the same way. You don't think about how to connect, URLs for, is this actor, remote actor, is it up? Has it been supervised? None of that. The semantics of your program does not depend on the number of nodes. Even if there are no nodes in the cluster, your program still runs correctly. Just slowly. But you never know when some nodes will connect or disconnect, and the semantics does not guarantee that. Okay, I will skip to the conclusion because I want to give you time for more questions. How am I doing with time? Okay. So basically, a declarative and almost purely functional. I shouldn't have said purely functional because emitting a molecule is an effect. Defining a reaction is an effect. Is not a value that you can referentially transparently put into an array or anything. Emitting a molecule is an effect. Other than that, things are purely functional. It's more purely functional than actors, for sure, significantly easier to reason about. I have an open source implementation. I'm planning to have some very good industry strength features. I have a tutorial book that explains how to work with it. And there are some interesting, promising applications, especially in workflow management, distributed peer-to-peer systems, and I'm working on getting the chemical machine to be distributed so that you can actually run it. Right now, I'm still in progress on that. The non-distributed version works. The distributed version is in progress. And I have some slides with technical implementation details. I'll just skip them. So thank you. Questions? So the question is, can I make it purely functional? Can I, instead of doing an effect immediately, can I return some kind of effect type from these things, from these functions? So can I have a function here that returns an effect type instead of actually executing the effect? Very good question. I have no idea how to do that. Maybe you can try to do that in some way, but right now I'm not able to give you an answer. So another part of your question was, what if it crashes? I would like to make it more resilient so that you can have error correction. So a concept of a reaction that crashes, and then something should happen if that crashes. So the first thing that I already want to do, and I know that it will work, is that if it crashes, then the cluster should know that this distributed data has not been processed. It's like a commit in the Kafka world. So if it did not crash, I commit. But if it crashed, I do not commit. And so that's kind of what I am thinking of doing. But or some kind of recovery, some kind of retry. I have a retry feature. I don't know if it's very useful. But that's what I'm trying to do. So I'm not going into the direction of purely functional because I don't really know how to do it well in this context. But this is a good question. Yeah.
Wondering, are the queues unbounded effectively for each mailbox? Then you can just
so the question is, are the queues for each mailbox unbounded? They are. However, the runtime can be made more clever. And so you can maintain counts of how many threads are busy and so on. And you can try to schedule fewer reactions or more reactions depending on how full mailboxes are. Right now, they're unbounded, and you can pile up a lot of unprocessed data. However, molecules are just little pieces of data on the heap with some wrapper. They're not threads. They're not heavyweight. They don't have their stack. Molecules are not like processes. They don't have stack. They don't have data, thread information. So you can pile them up pretty big, and so there is a lot of research on queuing theory, which tells you what is the capacity of a queue and when you can expect things to be done and so on. Maybe you can just and since in this kind of setting, your entire computation structure is known in advance, you can reason about it before you run it, and you can decide to monitor this reaction because it's got this input-output problem or something like that. So I think that's a good way of solving this problem, rather than making a mailbox bounded by some random amount.
When you have a computation of our network more expensive, so when you have, is there a mechanism to favor of it. For the local processing over the one.
Okay, so the question is there any mechanism of favoring one kind of reaction over another in case of determinism, for instance, to favor a cheaper reaction or to favor a local reaction over a distributed one? Right now, there is no such mechanism. For various reasons, it's probably not productive to have priorities on reactions. However, local reactions can be very easily preferred to distributed ones, which is probably what I'm going to do. The problem is you don't know when reactions start. And when you don't know that, and you think that a reaction will start because it has a higher priority, you're going to be mistaken. You're going to have race conditions.
Yeah. The idea is more to optimize.
Okay, so the question is, can we optimize the... my goal is right now to optimize the CPU usage. And that's what I'm going to do with thread pools and so on. I'm not going to prefer one reaction over another. So right now, I don't want to put weights on reactions and have some... But in principle, you could just say, well, this reaction has a higher value to us, and we would prefer to run it. And maybe you can schedule it first and prefer to... You can try to do that. And it will certainly be dangerous to use that mechanism in order to make your business logic work, because that's a race condition right there. You know, yeah, sorry.
Can reaction sites have conditions on the values associated?
Yes, the question is, can it have conditions on values? So yes, it can. It's a Scala partial function, can arbitrary things. You can have guard conditions, match, pattern match, and whatever you want, yeah. We are out of time. Thank you very much.